Usually when we pull research for these deep dives, we're looking at these really serious sounding terms, right? Quasars, asymptotic giant branch stars.
High-level stuff.
Exactly. High-level, serious astrophysics branding. But today, I think the most important term in our stack is a vegetable.
It is.
We are talking about green peas. And before you roll your eyes, these things are, currently rewriting the history of how the universe woke up.
It is arguably the worst name in astronomy, which is that's saying something. But you're right. If you can get past the salad metaphor, these peas are actually one of the most significant discoveries of the last, 20 years?
Oh, easily.
They're compact, they're violent, and they are essentially time machines just parked in our own galactic backyard.
Okay, I absolutely want to get to the time machine part because the JWST data on that is it's mind-bending. But we have to start with the discovery.
We have to.
Because this is the part that always gets me. This wasn't found by some, fancy algorithm or a $10 billion government project. This was a couple of people staring at their laptops.
Exactly. This goes back to 2007 and the Galaxy Zoo project.
Right.
The whole premise was simple. The Sloan Digital Sky Survey had taken 1 million images of galaxies, way too many for professional astronomers to classify by themselves.
So they just opened it up?
They uploaded them and asked the public to help sort them out, is it a spiral, elliptical, a merger, that kind of thing.
Which is just a brilliant use of crowdsourcing.
Yeah.
But then you get this user, Night Blizzard, who kind of stops the assembly line.
Right. In July 2007, Night Blizzard posts in the forums with a very specific problem. They'd found these objects that they didn't fit the buckets.
They weren't spirals, they weren't ellipticals.
Nope, they were just these bright, unresolved green dots. And Night Blizzard just asked, what are these?
And I love that instead of just, dismissing it as a glitch, the community just mobilized. I saw the forum thread title was, Give Peas a Chance.
Yeah. Started by Henny Van Arkel, who is an absolute legend in citizen science.
A legend. Right. And they formed the Peas Corps.
They did.
They dug through all the data and found over 100 more of these things. And it turns out the green wasn't some camera artifact. It was a physical signature.
That's the key. To the human eye, looking through a telescope, these wouldn't actually look neon green.
Okay, so what's happening?
The color is a result of how the SDSS telescope filters light. It all comes down to redshift. These galaxies are sitting at a redshift of somewhere between 0.1 and 0.3.
So they're moving away from us, but they're not at the edge of the universe or anything.
Correct. They are relatively local, but what makes them so special is their chemistry. They have this incredibly intense emission line of doubly ionized oxygen, what we call OII.
Which implies extreme heat, right? To strip 2 electrons off an oxygen atom, you need a serious energy source.
Massive energy. We're talking temperatures over 30,000 Kelvin inside these gas clouds, and usually that OI line is in the blue-green part of the spectrum.
But the redshift changes that.
Because of that specific redshift, the line gets stretched, it gets shifted right into the R-band filter of the telescope, which normally captures red light.
Oh, I see.
And the signal from that one line was so overwhelmingly bright, it just blew out the filter. The composite image just screamed green.
So it's basically an emission line galaxy that is just working way too hard for its size.
Working too hard is the perfect description. I mean, when the pros finally took a spectrum of these things, they realized they were looking at something truly extreme. These galaxies are tiny, maybe 16,000 light years across. Max.
And for comparison, the Milky Way is what, over 100,000?
Oh, easily. In terms of stellar mass, a green pea is about 1/390th the mass of the Milky Way. It's a speck.
A tiny speck.
But, and this is the kicker, it is converting gas into stars at a rate of about 10 solar masses per year.
Okay, let's just pause on that for a second. The Milky Way, our giant spiral galaxy with all its immense gravity, only does about 2 solar masses a year. So this little green dot is almost 400 times smaller than us. But it's churning out 5 times as many stars.
It is the most active star-forming environment in the local universe. If the Milky Way is a sedate, sprawling city, a green pea is a nuclear reactor in meltdown.
Wow.
This specific star formation rate is completely off the charts. If you were standing inside one, the sky would be blindingly bright, just filled with massive short-lived stars going supernova constantly.
And that intensity, that's what leads to the whole time machine theory.
Yeah.
Because looking at the data, standard cosmology would say that galaxies like this shouldn't really exist nearby. They look primitive.
They do. In the local universe, galaxies have had 13 billion years to sort of settle down, use up their gas, and become metallic and organized. But green peas look like they just woke up. Dr. Kevin Shawinski, one of the Galaxy Zoo founders, realized that these look exactly like the galaxies we expect to see at the dawn of time.
The living fossils.
Right, and for years that was the hypothesis. These are local analogs for the early universe, but we couldn't really prove it until we could actually see the early universe clearly.
And that's where the James Webb Space Telescope comes in.
Enter JWST.
This is that Rhodes paper from 2023.
Yes, this was the smoking gun. JWST looked at galaxies at redshift Zs, around 8. That is deep time. We're talking just 700 million years after the Big Bang.
So we're actually looking at the infant universe.
The actual infant universe. And when they analyzed the chemical fingerprint of those ancient galaxies, they overlaid them with the spectra of our local green peas. Identical.
That is wild.
It's incredible. It means we don't have to guess what the early universe was like based on these, fuzzy pixels from 13 billion light years away. We have laboratory specimens right next door. We can study the green peas to understand the physics of the Big Bang's aftermath.
And that brings us to the fog. Because if these are analogs for the very first galaxies, they solve a massive cosmological problem. The cosmic dark ages.
The epoch of reionization. This is one of the holy grails of cosmology.
So just to set the scene for everyone. After the Big Bang, the universe cools down. It's filled with neutral hydrogen gas. It's totally opaque.
Like a thick fog. No light can travel far. It's a literal dark age.
Correct. And to turn the lights on, to make the universe transparent like it is today, you need to ionize all that hydrogen. You have to blast those atoms with high-energy UV photons to strip their electrons off.
But the question has always been, where did that energy come from?
The candidates were always quasars or massive stars, but the math never quite added up, did it?
The math was tricky. We knew massive stars produce that UV light. We call them Lyman continuum photons. But galaxies are usually very good at keeping that light trapped inside.
The hydrogen inside the galaxy just absorbs it.
It absorbs it before it can escape to clear out the cosmic fog. We're self-contained. The Milky Way doesn't leak much UV.
So it's ionization bounded.
That's the term, yeah. The gas traps the light. But the green peas, they are what we call density bounded.
Meaning they have holes in the fence?
Exactly. Because the star formation is so violent and so concentrated and the gas density varies so wildly, these green peas are leakers. A 2016 paper in Nature looked at a specific pea, J0925, and found it was leaking about 8% of its ionizing radiation straight into deep space.
Which, okay, 8% sounds low, but on a cosmic scale, that's a flood.
It's enough. If the early universe was populated by billions of these tiny, leaky, angry little galaxies, they absolutely would have provided the energy budget to re-ionize the entire cosmos.
So the reason we can look up and see the stars today is likely because swarms of these green peas burned away that fog 13 billion years ago.
That is the leading theory. And other work using Hubble has backed this up, showing the specific mechanisms like channels in the gas that let the light escape. It's this beautiful piece of detective work connecting a glitch on a forum to the very structure of the universe.
Now, speaking of classification, that green pea name,
Yeah.
it unfortunately started a trend. In the notes, I'm seeing blueberries, purple grapes, and now little red dots.
And
It feels like we're just categorizing fruit, but these distinctions actually matter for the physics, don't they?
they do, though I admit the naming convention is getting a little out of hand. The blueberries, which were defined around 2017, are essentially the little siblings of the peas.
Even smaller.
Much smaller. We're talking less than 1/3000th the size of the Milky Way. But they are even hotter and younger. They represent sort of the extreme lower limit of what a galaxy can be and still have a massive starburst.
But the one that really caught my eye is the little red dot. This is a JWST find, isn't it?
This is brand new science. JWST found these compact red objects in the early universe, about 600 million to 1.5 billion years after the Big Bang. They look like the ancestors of green peas, but there's a twist.
The black holes.
The black holes. The spectra of these little red dots suggest they host active galactic nuclei supermassive black holes that are actively feeding on gas.
And that complicates the picture, doesn't it? Because we thought green peas were just star factories. But if they're the modern descendants of these little red dots...
It implies that some of our local green peas, specifically the ones with broad spectral lines, might be hiding intermediate or even supermassive black holes that we just haven't properly identified yet. It blurs the line between a starburst galaxy and a baby monster.
So a green pea might not just be a star factory. It could be a casing for a growing black hole.
It's very possible. And this feeds directly into the metallicity debate that's been raging for a decade.
Okay, walk us through that, because originally Cardamone, who wrote the first big paper on this, thought they were metal-rich, right?
Yes, the early assumption was solar-level metallicity. In astronomy, metals are anything heavier than helium. So if a galaxy is metal-rich, it means previous generations of stars have lived and died and enriched the gas. It implies age and recycling.
But then Amarin came along a few years later and said, no, check the data again.
Right. Amarin and then others argued that Ps are actually metal poor, about 20% of solar levels. And this is crucial because it explains how they fuel the fire. If they're metal poor, it suggests they are accreting pristine primordial gas from the intergalactic medium.
This is the cold accretion theory.
Exactly. They are sucking in pure, unpolluted hydrogen from space, and that's what fuels that insane star formation rate without adding heavy metals. It supports the idea that they really are primitive engines.
But here's where the physics just it breaks for me. We have these primitive, chaotic, messy galaxies, and yet when we look at their magnetic fields, they just don't make any sense.
The magnetic mystery. This is my favorite part of the whole puzzle because it challenges our fundamental understanding of how galaxies even work.
Okay, so the standard model is dynamo theory.
The dynamo theory basically says that magnetic fields in galaxies are created by rotation and turbulence over billions and billions of years. It's a slow build. A young, small galaxy should have a weak, disorganized magnetic field.
The Milky Way, for example, has a field strength of about 5 microgauss, and we've been spinning for eons.
Correct. But then Chakraborty and his team looked at the radio emissions from green peas. They found magnetic fields exceeding 30 microgauss.
That's 6 times stronger than our galaxy. In a galaxy that is, for all intents and purposes, an infant.
It shouldn't be there, not according to the slow-growth dynamo model. It shouldn't be possible.
So what's the explanation? I mean, how do you get that kind of magnetic power basically instantly?
We think the star formation itself is doing it. The sheer violence of the supernovae explosions might be driving what's called a fast dynamo, amplifying the magnetic fields exponentially faster than simple rotation ever could.
So they're so violent that they are bootstrapping their own magnetic shields.
Essentially. And this really matters, because magnetic fields dictate how stars form. They regulate the collapse of gas clouds. If young galaxies in the early universe had strong magnetic fields, which the Ps suggest they did, then our simulations of the early universe might be completely wrong.
So we might be underestimating how organized the early cosmos actually was.
We could be, yeah. It seems like every single time we look closer at these things, they just break a rule. They leak when they should trap light. They have magnetic fields that are way too strong. They might be hiding black holes.
It's the beauty of extreme objects, I guess.
Yeah.
They stress test our physics.
That's a perfect way to put it.
So, zooming out. We started with a forum post about a green smudge, and we've ended up with a model for the reionization of the entire universe and a direct challenge to dynamo theory.
It really just highlights the blind spots in how we process data. We build algorithms to find what we know, spirals, ellipticals. We train them on established physics.
But the universe doesn't care about our training sets.
It really doesn't.
Yeah.
If Night Blizzard hadn't posted that image, or if the Peace Corps hadn't manually dug through the archives, these things might have been filtered out as noise for another 20 years.
It makes you wonder what else is sitting in the trash folder of these massive surveys.
Oh, almost certainly there are other classes of objects we haven't even defined yet.
That's a haunting thought.
It is. I mean, if green peas are living fossils that somehow survived to the modern day, there could be other relics hiding in plain sight, dismissed as artifacts just because they don't fit the pattern we're looking for.
Well, I think the takeaway for our listeners is pretty clear. If you're scrolling through data and you see something that looks like a vegetable side dish, do not delete it. It might just explain the Big Bang.
Give peas a chance.
Had to end on it. Thanks for listening to this deep dive. We'll see you on next one.